To wrap up our video on regression, let's talk about some assumptions of linear regression. So when we have a linear regression, there are assumptions we make about the residuals or the error. So our linear regression assumes a linear relationship between our independent variable. So in the last couple of videos, that's been the age of the car, and the dependent variable, the repair costs. We are assuming that they either move together, move in opposite directions, or have no relationship, but we're looking at a linear relationship. There are other types of regression that are not linear, logistic, Poisson, and if you watch our videos in the business and analysis playlist, or if you're working through one of my courses, as we get to more predictive prescriptive analytics, we'll come back to those types of regression models that are not linear. So we're assuming here that with linear regression that we have a linear model, and that means that the linear relationship is going to explain that, and they have an appropriate model. But the other assumptions that we make are that the errors have what we call constant variance or homoscedasticity. Homoscedasticity means that the variability stays the same. It's homogeneous. It has an average of 0. But that as you move through the data, it doesn't get to be more variability from where there was less or less more. Like it's the same level of variation throughout. The errors are independent. They don't depend on each other. And the errors are normally distributed. So let's take a look at some residual plots and let's talk about these assumptions. All right, so what we do is we plot the residuals. The residuals look at the difference between the actual and the predicted values. In our video 2 videos ago, when we did our original request in Excel, so just go back, we went to, let me pull this down. In our data tab, let me pull my face down too, here we go. All right, so in our data, when we had our original data set, we had gone to, all right, we started here. When we were here, we went to our data analysis tool pack and we went to regression and we asked for a residual plot. Okay, that request for the residual plot then gave us, if I back out of that, that gave this plot here. Okay, so our residuals and our different values here of our x variable. So when we look at this residual plot, what we are looking for is random scatter. It should look like just a bunch of noise. They should look like they're randomly placed. When we look, let's go back here. When we look at that, we are looking for it to be randomly scattered around 0. We are not there should be no noticeable trends or patterns. Okay. Now, what do we mean by no patterns? So this looks like a random scatter. If you see that your residuals have, say, this bend here, a clear pattern, then we've chosen the wrong type of regression. So this shouldn't be a linear regression because there is this relationship in the data that's not captured by our linear relationship. So maybe a polynomial would be more appropriate given the fact that this goes up and then down. The other thing we look at is that we look at whether or not we have homoscedasticity, so constant variance, or heteroscedasticity, non-constant variance. So notice in this particular example that the residuals here are much bigger than here. Okay. That there is an issue with our linear model then because we don't have that constant variance. The other thing we might look for is a pattern that looks like this. That's telling us that we may have some seasonality, for example, to our data. So it's autocorrelated. There's a relationship between the residuals. They're not independent of each other. That means that the previous residual is going to be able to be used to predict where the next residual is. These all require different models from linear regression. We're going to talk in later models about SARIMA models. They have seasonality in them. We're going to talk about polynomials. Okay, these models capture some of this. So if you are starting to see in your residuals that it's not a bunch of random scatter, but there are patterns, that can indicate to you that there is a better model out there. The linear regression should look like random scatter. If you have a pattern, then perhaps you should be using a different model for it. Okay. So we are looking for that it is random scatter, that it truly is a linear relationship. If the errors are not independent, we are going to see that autocorrelation. If the errors have non-constant variance, so they are heteroscedastic, it's going to look like this. Okay. We're looking for the errors to be independent, have constant variance, be normally distributed, and have a linear relationship. So you're looking for no patterns in that data. If we violate the linear relationship assumption, there's going to be a pattern like this here, this polynomial. If it violates the homoscedasticity, then it is going to have the fact that residuals get bigger or smaller. If the errors are not independent, then we're going to have that seasonality, these cycles to it. Okay. And so we're looking for random scatter. We can also see, if you see there might be some extreme values, like a one-off extreme that's much bigger than everything else, it might also be an indicator of an outlier. In later videos, we're going to look at different methods for identifying outliers in your data set. One way to deal with outliers in your data set or identify them is to do a linear regression. Create that line of best fit. And then because we know from the standard error of estimates that we should have a normal distribution, anything that is too far outside, I don't know why I just wrote a 3 there. Anything that's too far outside, maybe it's more than 3 standard deviations away, would be flagged as a potential outlier. You could decide how many standard deviations are how conservative you want to be in flagging your outliers. So we can use our linear regression and the fact that that standard error of the estimates has a normal distribution to flag any extreme values. You can also look in your residuals plot for any potential outliers and double check, is it a typo? Is this number supposed to be something different? Do you know what the actual number is supposed to be? If it is a number that's not even possible, you're asking about people's ages, and the age that you have in your data set is 300. You know, maybe it was supposed to be 30, maybe it was supposed to be 3. We'll talk about cleaning data in future videos as well. So if you go see the Business Intelligence and Analytics playlist, or you continue through one of my courses as we work through prepping our data, then we'll talk about cleaning the data for ones that are clearly typos. Do we know what they're supposed to be? Or if we don't, we remove them. We don't remove all the data. We just remove that particular data point in order to do our later analysis. So we're building on all of this now that we know the foundations of some of the different methods in statistics. So this is showing you the residual of Tiger trucking. So I just want to take you to, I guess I'll do that in Excel. And so, getting ahead of myself. Okay, so, sorry. What are we doing? Okay, the other thing we talked about in assumptions, before I just, get off on random tangents, is the fact that the underlying data is normally distributed, so the residuals should be normally distributed as well. We talked before about how to check for normality. We talked about how to check for normality in our sample using a QQ plot. We can check for normality in our residuals using a QQ plot. So in Excel, here is a normal probability plot. The ones in Excel are terrible. We talked about before that Excel doesn't make a QQ plot on its own or in what we were looking at previously, which is trying to check normality for our hypothesis tests and confidence intervals. It does it here in regression, but it's really hard to read. Like, you're looking for that it follows a 45-degree line. How did I get this QQ plot? Well, when I was originally here and I went to data analysis and I went to regression, I could choose here a normality plot. Okay, so that's giving me my QQ plot. Now, let's get our QQ plot and our residuals in Python. Let's take a look at how to do that. Okay, so we're going to test our assumptions to our model. We're going to import skippy.stats as stats. We're going to import matplotlib.pyplot as plt. This is the third video in our discussion of regression. So if you are just joining us, please go back to the regression video for how to access this workbook and the data itself. So you kind of need to go to the regression video to get the data and the first part of this workbook, and then we're just continuing through. But you have access to this, as I just very briefly mentioned. You have access to this workbook by going to drstephpowers.github.io/BIA, and here we are in regression. Go to GitHub, open in Google Colab, also get the stats3 data set here, download it, dump it into your Google Drive, and then work through, as the regression video, connecting your workbook to your files so that you can run the code. Okay, back to our code. Import skippy.stats as stats, import matplotlib.pyplot as plt. We had already run our ordinary least squares regression using SMF. We did an ordinary least squares. We were predicting Y using X from our data set that we had named reg. So we had renamed repair costs and age just to keep us straight. Okay, so we have this. We use this to build our model. We outputted our model, we summarized it, and we looked at how to use that information in the last video. Once we've done all that, we can check the assumptions here by having it output the residuals from that regression. So we're going to call these res. We are going to take the model we called OLS_reg, and we're going to have it output the residuals. Okay, once we have the residuals, we can then use the package we had installed previously, which was import statsmodels.api as sm, to create our QQ plots. So make sure you've run this here so you have sm. If not, it'll tell you that it doesn't know what sm is. And so what we're going to do is create a figure using our matplotlib.pyplot as plt. We're going to create a QQ plot of the residuals, have it compare it to the t distribution. So this stats.t comes from this skippy.stats, telling us what the quantiles are for a t distribution. And then when we do this, what it's going to do has no attribute t, because what did I not run? Stats. There we go. Don't run your packages, it won't work. Okay, so it gives us a plot. The sample quantiles are from our residuals. The theoretical quantiles are from the t distribution from that skippy.stats. And if it is normally distributed, it should follow along the 45-degree line. We've looked previously. If you see that you have kind of this up and over curve, then you're not normally distributed. So we're checking the assumptions of our linear regression model. Our residuals should be normally distributed. Okay. We can plot the residuals themselves, just like we did in Excel. We can use the same plot method we use with scatter plot. I'm simply going to add a horizontal line at 0 because we know our residuals should randomly scatter around 0. So we're going to use matplotlib.pyplot as PLT. That's this right here. We imported this to make this run. So then we can use plot from PLT. We're going to plot the residuals, that res that we had it calculate for us from our ordinary least squares regression. And then we are going to have markers equal 0, line styles equal none. We don't want lines, we just want dots. X-axis, we're going to call residuals. As I said, we're going to add a horizontal line. So this AXH line adds a horizontal line to our graph. We just need to tell it where. So it's going to be at y equals 0. And the color, you can make it a different color. Here's black, line style line. There are different symbols. You want dashes and stuff like that you can choose from. And then output the plot. So what I am looking for is random scatter around this line 0. There should not be a pattern, right? We should not see any dips. It should be random. And we should have homoscedasticity, so the amount of variability. See how at lower values of we get, so left of the graph, it goes up to 40, and then we have variability here, and then later on it goes back up to 40 again. So you can see that that variability is the same. There's maybe a little bit of difference here. We don't have a lot of data. So be careful as you're looking at residuals. The smaller your data set, the more you're likely to kind of look, oh, there's a relationship, a pattern here. Well, it could simply be the fact you don't have a whole lot of data. So one more data point would have put you right there, in which case the variability would be the same on the left side of the graph as the right. So be careful that your small sample size might infer relationships and patterns that aren't necessarily there. All right, so just to recap, where we've been, what are we doing? I don't know. All right, our errors should have homoscedasticity. The error should be independent. They shouldn't have any patterns. The error should be normally distributed. Those are the assumptions we make when we're doing linear regression, so we double check that, because if we are violating those assumptions, then we are using the wrong type of regression. Likely there is some other relationship. Maybe it's not linear. We are less likely to have some of these issues if we check the correlation first and we have highly correlated, linear correlated data. Then we're less likely to violate these assumptions. So check that first. But then also check your assumptions as you create your linear regression model to make sure you're not missing something else important that's happening in your data. I'm just going to leave you here with one more data set. So if you are in our Python data, we have a data set here called Tiger, and you can import it into the data set and perform linear regression with it. Check to see what is the model, how well does it fit, does it violate the assumptions that are made, can you come up with confidence intervals, can you make an estimate of what let's just go and before I get too far ahead of myself, let's just go to the original data set here. Oh, look, here's all the answers. All right, where are we going? There we go. Okay, Tiger Transport Trucking Company is concerned about the prices charged for moving small loads over long distances. It has rates it's happy with for the full truckloads. These rates are based on the variable costs of drivers, fuel, and maintenance. Okay, when a truck is less than fully loaded, however, there is some question about the proper rate to be charged on goods needed to fill the truck. Tiger feels that the additional costs incurred if additional cargo is added to the truck is the cost of additional fuel, since the miles per gallon of the truck would then be lowered. So we're looking at the relationship between miles per gallon and weight. We wish to estimate the out-of-pocket costs of additional cargo to assist the cost accounting efforts. And so we would like a formula that will take weight as the input and return an estimated miles per gallon. So you're going to come up with a formula for y hat, where y hat is the miles per gallon You're going to find the formula b times b0 plus b1x, where x is the weight. And from there, you can create confidence intervals, prediction intervals, check your assumptions. How good of a model does this fit? What is your R squared? So your coefficient of determination. How much of the variability in weight explains the miles per gallon? How good of a model can you create? So I'll leave you with that. In order to create the model here, we have the data set, whether you're doing it in Excel here, so you can create your model in Excel, or you can create it here in Python. So give those a try and see if you can build your regression models.